So in this video, I'm going to show you how to design the mat foundation based on the support reactions that were provided by the steel structural engineer. So here we're going to look at design of concrete pedestals, concrete slab on grade, and this whole process is going to be based on the concept of a seed file, or if you try to do automation in your design group, this is going to work out best for you. Okay, so let's talk about what are the steps involved. Okay, the first step is to create your model geometry. In this case, we're going to go and create a very simple geometry using the model wizard tool. You can create it using the base plate wizard, or you can create it using GT menu. But then we're also going to go in and create these groupings. Okay, now the groupings are going to be used to assign supports to your nonlinear supports to your mat foundation based on the subgrade modulus. You can use these plate groups to also assign these nonlinear supports or curves to your node points. We're also going to create this pedestal group to design our pedestals. Then we are going to reference our support.gti file that is going to generate the supports based on these groups. Loads.gti file will contain all the loads that are coming in from the steel structural engineer, and also contain all the predefined load combinations as per the code. The analysis is going to contain all the analysis commands. The design is going to contain all the design commands. So you could go in and use this command called cinput soils.gti, and it'll actually create the supports for you, okay, soil supports for you. But if you wanted to consolidate everything into one GTI file, you can do that as well. In this demonstration, we're going to use two GTI files. I'm going to create one for generating the soil supports and the other one for generating loads, analysis, and design results. Okay, so first we obtain this file from the steel support structural engineer, right? So we get all these loadings. We can just copy all these loads, okay, just everything that he sends you, he or she, and then you can actually go to your loads.gti file that I'll just show you. Okay, we have already created one in this presentation, so let me just open up Explorer, and here, this is the file that I have, and you can open it using any Word or Notepad file, and you can just select all the loads and just copy and paste, Control V. Okay, so anything changes on the structural side, all you need to do is just copy and paste those. These node numbers are basically coming in from the steel structure. Okay, so you can easily reference where these loadings are coming from. Then we apply the self-weight loading. We create these load combinations per the code. So everything is contained in this one single file, and this is called the seed file, which is basically going to avoid the engineering group from creating these load combinations over and over again from project to project or structure to structure on a single project. Okay, we have defined all the nonlinear commands here. Okay, we can activate these using the graphics also, but here everything's copied from the shell environment to this file. And then we have design commands based on the pedestal group that I just talked to you about. And then we have slab design commands as well. Okay, so let me save this file. And now, first, I'm going to launch GT STRUDL and create the foundation geometry. Okay, so again, GT STRUDL 41. And here, what I'm going to do is first launch the model wizard tool. inside the Model Wizard tool, we have an option called Finite Element Mesh. I'm going to click on OK, click on Next. Accept these defaults. The foundation is 2.5 feet thick. I'm going to give the mat foundation dimensions. It's very hard to actually show you the design of the foundation in less than 15 minutes, but I'm going to try my best to do that so that you get some idea and tips to start your next foundation design project, okay? So here I'm going to say, okay, I want 40 by 40. So this is the FEA mesh that we've created. Let me just go back and check. Okay, now this is the orientation of the mat. The orientation of the mat should be XZ because the Y-axis is the axis of gravity for the steel structural engineer. So we want that to be true for the mat foundation as well. Then we go to next. Here I'm going to pick SPHQ6 element for design of my mat. Click on next, and I'm going to assign soil compression only springs, and the subgrade modulus is 3,600. Next, and if we click on finish, it'll create this file for you, and you just saw the preview. Now, when it creates the file, it also gives you some tips as to what it's doing, and if you wanted to check out some nonlinear curves, it'll tell that okay, you can take these commands and type those in, copy and paste them here, Control C and Control V here, and you can see load versus deflection. Okay, but what we'll do here is we will go in and save this file. Okay, we can just go File, click on this pointer on the right hand side of the disk, and we can just say Command History. Okay, and we can just save it in this directory. Okay, now on the other hand, since we've used the Model Wizard tool, the Model Wizard tool automatically creates this planar element mesh wizard.gti file. Okay, so you can refer to that file as well. So what I'm going to do is I'm going to exit out of this environment and actually open up that file using any notepad editor. Okay, so we see all the node coordinates here. We have member incidences, okay, as we scroll down. And at the end, we have some commands, okay? Now, these are the commands to generate the soil springs. But really, we don't want to generate the soil springs at this point because we've decided to divvy up the file into 3 parts, okay? So the first is going to be geometry. The second one is going to be supports. And then the design and analysis commands, okay? So I'm going to take off those just to simplify this file. Also, the structural engineer has given us the location of the tank base plates, okay, XYZ coordinates of that. So what we can do is we can come down to these end of the node coordinates, and we can go back to our Excel file that we had. And in this Excel file, you see all these IDs, XYZ coordinate, you put Control C and Control V. Now you can also do that using the graphics or the data sheets. I'm just showing you another way, okay? As long as these node numbers don't conflict, you're fine. But if it starts conflicting, then you may have to, ask the maybe rename those nodes that are given to you, or ask the structural engineer to rename his nodes, put in an alphanumeric value, let's say S in front of those IDs. That'll also work. Okay, so now we've done this copy and paste. Let's open up that file, okay? For that, we'll go into GT menu now. So first, we will go in and connect the try to create the pedestals. Okay, so we'll go to GT menu now and open up that file. Go to File, Read Input File, and the file that we just modified was planar element mesh wizard.gti file. And there's the file. Okay, so here, this is giving you the elevation view. Okay, so you see this is the mat, and this is these are the nodes for the tank. Okay, now the reason why they're up in the air is because here, if you look at the coordinates that the structural engineer has given us for the base plate, it's at 4 feet. Okay, the mat is about 2.5 foot thick, right? So really, the height of the pedestal would be that distance minus half of the depth of the slab, and that should be 2.897. Okay, so let's draw those pedestals here. So I'm going to press I on the keyboard and zoom it, so you see that circular pattern now of these where these pedestals are supposed to be located. You can just go to Create, Place Elements. Here I'm going to say that, okay, concrete is fine. The section property, I'm going to go select a concrete cross section, let's say circular profile, 34 inches, store that, and we'll just say start and end direction. 2.897 is the distance along -y, okay? So now let's draw the pedestals. So pedestals are going to go here, this location, and so on, okay? Now, one thing that you need to keep in mind is this is finite element analysis that we're doing, okay? Which is an approximation to the actual conditions on the site, okay? So it is not an exact science. The other thing is how the load is going to get transferred from these pedestals into the slab is, it's not going to be like through one node point. It's going to be a thick foundation, so the load is going to get distributed, okay? Finite element analysis right now is not capturing that type of behavior. So what we need to do is to model rigid links, okay? Which is a very common practice. So what we do is we create a stiff element type here. And that stiff element type would have, let's say, modulus of elasticity of steel multiplied by 10, okay? And I'm just going to store stiff. And you can see this is exponent 6, this is exponent 7. Click on done. Now, for that rigid element, I'm going to pick a concrete cross section, let's say 16 inches. And then I'm going to draw that rigid link at these locations, okay? Now, if I mean, there's several ways you can draw in using this element tool. You can just say specify start and end. Okay, this is the easiest one. We can just specify the start and end, and we can just draw a link from the bottom of the pedestal to some adjoining nodes. Okay, so in this case, I'm going to pick 4 of them. But you could go in and attach it to any number of points, okay, so that you're distributing the axial load that's coming in from these pedestals to an area and not just a point, okay? If you have it going through a point, it's like a needle piercing through a piece of paper, and you will actually see very high stress concentration at the location where where the pedestal actually meets the slab, okay? So this will go in and actually distribute it nicely, so your slab is not designed too conservatively, okay? Okay, so this is a little bit of work, okay, but we're almost done. As you can see, I'm on my last pedestal. You can come up with some creative ways to automate the drawing of these pedestals. Okay, again, this is not an exact science. It is finite element analysis, and it's an approximation to the actual site conditions. Okay, now if you look at it now and look at it in 3D, okay, now you can see those circular pedestals, and then you see these rigid links connecting to the slab. Now, what this allows us to do also is have a nice quadrilateral mesh for the slab, and also we can go in and interpret these results. If you wanted to do any hand calculations, that should be easy enough to do with quadrilateral plate elements. Okay. Now, once that's done, we can go and now create those groupings that I was talking about. First group that I'm going to create is the node group. Okay, so we can go to create groups, add new, and I'm going to call this group called S nodes. Okay, and this is just going to be the nodes of the foundation. Okay, so I'm just going to go X, Y, and we're just going to say fencing, and we're going to say joints, and we're going to draw a really thin window. Don't include the pedestals, just the slab node points. Okay, so that's done. Now we're going to add another group and call it plates. Okay, so this is actually going to be all the plates or elements that we have modeled. So again, I'm just going to go to elements and draw a very thin window here, fence around, and here we go. We have the entire slab. Okay. Now we're going to create a new group, call it PEDES. Okay, pedestals group. And this is just going to be all the members. I'm just going to say include completely or partially enclosed items. Okay, so I'm just partially going to enclose these pedestals. It'll automatically pick those. And we've created the third group. Okay. Well, so once you've created the group, you can just go to File, Generate GT STRUDL File, Generate Input File, and you can just replace the file that we already have, save this file, or you can call it a different name. And if you double click on it, this is how it looks like. Now you have all these groups, right, in it. Okay, so now let me go back to that Word file that had all my steps in it. Okay, just to recap, we've created our models, we've created our groups. Now we need to reference our soils.gti file and our load analysis design commands. Okay, so I'm just going to Control C all those commands and put it into this file. Okay, and close it. So now the magic starts. Okay, we have automated the design of the mat, foundation, pedestals, and even the slab using this seed file. If you want to make any modifications, we just go in and modify the text file, and we're done with the design. Okay, so let's see this in action now. So let's go to GT STRUDL 41. To open up that file, you can go to GT menu, open it up using the graphics, and we can just go GT menu, and we will open up that file that we just modified, file, read input file. And this is the file that we modified. And if we click on open, it'll go in, read the file, run the nonlinear analysis, as you can see here. It'll go in and start the design of the pedestals. And this is the reinforcement for the slab. Okay, let me click on done. Now, here, if I show you the 3D view, if you go to results, deform shapes, this is actually showing you the deformation of the slab due to load case 101, okay? But remember, we also have a self-weight loading case. So this is like self-weight off the mat plus the loading of the steel structure. And this is both combined, okay? So you see, this is the actual behavior of the slab because of its own weight and the weight of the steel tank. If I stop that and go to results, finite element analysis results, stress contours and strains, you can see the stress contours. I can just go to bending resultants, okay, and you see the bending moment in the slab due to that load case. You can see where those maximum bending moments are. You can grab that plate number and you can say, hey, just design that plate for me, okay? And show me the rebar. That's exactly what I did, okay? And you can take a look at the file that I have created. I'm going to send you all those 3 files with the Excel spreadsheet and the Word document that I've created so that you can try it out on your machine too. Let me exit out of this menu interface and come to GT Shell. Okay, now in GT Shell, it went in and designed every single pedestal for you based on ACI 2019 code. Okay, so if you see, if I show you this, it's ACI 318 2019 code, tells me for this pedestal what is the spiral reinforcement and the capacity, what bar sizes, and so on, okay? So that wraps up the design of the foundation in GT STRUDL based on support reactions that you obtain from the structural engineer. Thank you.